Today, we're going to talk about a really fundamental technique for building machine learning models that actually work in the real world. It's called regularization, and we're going to focus on the two most common types, L1 and L2.
First, we'll start with the problem that regularization was born to solve, overfitting. Then we'll get into the core idea, which is basically a penalty for complexity. From there, we'll unpack L1, which acts like a feature selector, and then L2, which is more of a weight shrinker. And to finish up, we'll cover how you actually choose between them for your own projects.
So, have you ever had this happen? You train a model and it performs perfectly on your training data. I mean, the scores are amazing, but the moment you show it new, unseen data, it just completely falls apart. It's a classic, and honestly, a really frustrating problem. So, what is going on here?
Well, this is a textbook case of something called overfitting. And by the end of this explainer, you'll understand exactly how to prevent it by penalizing your model's complexity using L1 and L2 regularization.
So, what is overfitting really? It's when a model learns the training data too well. So well, in fact, that it starts memorizing all the noise and the random little quirks in your specific dataset, instead of learning the actual useful pattern underneath. And because of that, it can't generalize to new data it's never seen before.
I think the best analogy here is studying for a test. An overfitting model is like a student who just memorizes the exact answers to the practice questions. Sure, they might ace the practice test, but on the final exam where the questions are a little different, they're going to fail. A good model, on the other hand, is like the student who learns the underlying concepts. They can solve new and unfamiliar problems because they've actually learned the material, not just memorized it.
Okay, so how do we push our model to be more of a generalizer and less of a memorizer? The solution is actually pretty clever. We just introduce a penalty for being too complex.
And that's exactly what regularization is. It's a technique that adds a kind of complexity tax to the model's loss function. This tax is based on how large the model's weights are. By discouraging big weights, we're basically nudging the model to find simpler, more general patterns, the ones that are much more likely to work on new data.
All right, let's look at our first tool, L1 regularization. The whole idea here is to penalize the model based on the sum of the absolute values of its weights.
So when the model is learning, its total cost isn't just about its prediction error anymore. We add this new term to it. It's a value called lambda, which just controls how strong the penalty is, multiplied by the sum of the absolute values of every single weight in the model.
Now, this absolute value penalty creates a really interesting geometric shape. You can think of it as creating a boundary for the weights that looks like a diamond. The model has to find the best answer, but its weights are not allowed to go outside this diamond.
So imagine the model is trying to find the point with the lowest prediction error, that's the center of those contour lines. It wants to get to that center, but it's stuck inside the diamond. Because of the diamond's sharp corners, the best possible solution is very often found right on one of the axes.
And this is the magic of L1. When that optimal point lands right on an axis, it means the value for the other weight is exactly 0. It effectively switches that feature off entirely.
The result of this is pretty powerful. L1 regularization, which you'll also hear called lasso, creates what's known as a sparse model. That just means a model with lots of weights set to 0. This is a huge deal, because it's basically performing automatic feature selection. It simplifies the model and makes it way easier to see which features are actually important.
Now for our second tool, L2 regularization. This one works a little differently. Instead of using the absolute values of the weights, L2 penalizes the sum of their squared values.
The formula looks almost identical to L1, but that one tiny change, squaring the weights instead of taking their absolute value, makes all the difference. The total cost is now the prediction loss plus lambda times the sum of all the weights squared.
Geometrically, this squared penalty creates a constraint boundary that isn't a diamond, but a smooth circle. The model's weights still have to stay inside, but now the boundary is round.
So as the model searches for the lowest error, the first point it touches on this circular boundary is very unlikely to be exactly on an axis. The smooth curve means the weights get smaller. They're pulled in towards the center, but it's rare for any of them to become precisely 0.
And this leads to a very different outcome. L2, or ridge regularization, creates a non-sparse model. All the features are kept. It just shrinks all their weights towards 0, which prevents any single feature from having way too much influence. You might also hear this called weight decay, which is a pretty good description of what it does.
Okay, so now we have these two great tools for fighting overfitting.
but they work in different ways. That brings us to the big practical question. When should you use which one? It really comes down to your goal. If you need to do feature selection, especially if you have tons of features and you think a lot of them are probably useless, L1 is a fantastic choice. It will give you a simpler, sparse model. But if you think all your features are probably useful and you just want to balance their influence, L2 is the way to go. It's also a bit better at handling features that are highly correlated with each other. Let's make this concrete. Say you're in genomics and you have data on thousands of genes, but you want to find the few that predict a disease. L1 is perfect for that. It will zero out the unimportant genes. Now contrast that with image recognition. Every single pixel could be important. You don't want to just throw them away. L2 is a much better fit there because it makes sure all the pixels can contribute a little bit to the decision.
So, to wrap it all up, regularization stops overfitting by putting a penalty on complex models. And here's the key takeaway to remember. Use L1 when you want feature selection and a simpler model. Use L2 when you want to keep all your features and just make your model more stable.